Good day, my dear students. It is fourth video on diffraction. First two videos are reference videos. In the third video, I explained diffraction and the two types of diffraction, namely Fresnel and Fraunhofer diffraction. Diffraction is the bending of light ray, and it is explained on the wave nature of the light. Light travels in the form of a wave, but still in common practice we see light travels in a straight line. If it is traveling in the form of a wave, then why we see light up is moving in the form of a straight line? It is moving in the form of a straight line. That is the rectilinear property. So now in this video we are explaining the rectilinear propagation of light on the basis of wave theory, right? Why the light appears moving in a straight line even though it is traveling in the form of wave. That explanation is given by Fresnel, and today we study that. The explanation of rectilinear propagation of light on the basis of wave theory. See this, our aim is to study rectilinear propagation of light. Okay, light moves in the even though light is moving in the form of wave, but it appears as if light is traveling in a straight line. That we have to explain, and this is a Fresnel explanation. Consider a plane wavefront, means a parallel ray of light. Okay, and you know this. A parallel beam means it is a plane wavefront. Okay, parallel rays means it is plane wavefront. So this is the plane wavefront, and we want to know what is its effect at a point B. At a point P, which is at a distance B from this wavefront. The effect of light at point B from this wavefront that we are considering now. To find the effect of light at point B, Fresnel said, let us construct the off-period elements. Off-period elements means with P as center, construct annular zones. What you have to do is you have to write annular zones with P as center around point O on the wavefront. So what I will do is the distance between O and P is a point on wavefront, right? Exactly, it is opposite to this, and this distance is B. Now I am constructing off period elements. They are called off period elements with P as center and the distance as B plus lambda by 2, where lambda is the wavelength of light, right? And with this radius, I am constructing off period elements around P. Next, another off period elements with B plus 2 lambda by 2. Like that, you have to construct off period elements around point P on the wavefront. Why we are doing this? We are explaining the rectilinear propagation of light, why light travels in the form of straight line, why it appears as if it is moving in the form of light on the basis of wave theory. For that you do this construction, and then we are explaining this. This is the Fresnel explanation of the rectilinear propagation of light. At point O, if you do like this, what happens? O is the point on the wavefront. Then we'll get this. this, and this is point P. This distance is B, this distance is B plus lambda by 2. Then we will get this B plus 2 lambda by 2, and this with B plus 3 by lambda 2, like that. So you are going to get these annular zones, and these are called off period elements or Fresnel zones. Off period elements are zones, right? And if you see this I will call as M1, this point, and this point is M2, this point is M3. And if you see this radius of first half period element, this is first half period zone, and this is second half period zone, and this is third half period zone. Okay, and this radius is OM1. The radii of period zones are OM1, then OM2, then OM3 are radii of period elements, right? Now we will study the effect of all these off period elements at point P. Okay, to do this, what we the two things you should remember: diffraction or interference are due to the superposition of the waves. See this, if this is the first wave, right, and if another wave starts, this is the first wave, if another wave starts from this, okay, identical but another wave, and this is, I will call this as a second wave, but second wave starts after a gap. What is the gap between these two? If both are identical, if this is the distance, this is O, this is A, right, this is B. So after a gap OA, or after a path difference means the gap between two, the distance between two waves. The second wave started after a gap of OA. If you talk in terms of the lambda or the wavelength of the light, then from this O to B is lambda. This is the distance. From O to A is O to A. OA path difference is lambda by 2. OA path difference is lambda by 2. So the second wave started after a gap or a path difference between first and second wave is lambda by 2. The second wave started after a gap of lambda by 2. This is path difference. If you say in terms of phase difference means, see, wave is one oscillation gives one wave, right? If it is O, this is A, this is B. This point is, I will call it as T, this as U. So this is O, this is a T, this is A, this is U, this is B. So what is the time taken? Time taken is for O to T, T to A to U, U to B, right? That time taken is capital T, time period. Okay, or you can make this a small t, don't confuse it, the time period. So T is a time period. What is the phase difference? Phase from 0 to T. If you talk in terms, this whole total phase is pi. Okay, this is pi by 2. Up to 0 to t means this. This is also equal to uniform circular motion. One wave, one oscillation is equal to one uniform circular motion. So it started from this is O, right? This is O. It started from this. It is T. It reaches U. It comes here and comes back to this is A. This is U, and it is coming back to B. From O to A means it is 180 degree, right? So O to A means 180 degree. So path difference lambda by 2 equal to phase difference of pi. So it is first wave is going downwards towards trough, whereas the second wave is going up towards crest when there is a path difference of pi. It is trying to go down and it is going up. Means this is out of phase by pi, right? When path difference is lambda by 2, the phase difference is pi. This is very important idea to understand interference or diffraction. And another one is obliquity factor. If you see the effect of a light wave from this point onto this is maximum. And if you take the effect of the light wave from this point to this point, it is smaller than this because it is oblique. If the light moves in an oblique way to this point, then the effect goes on decreases. Again, this effect is lesser than this effect is lesser than this. This has got the maximum effect. This is on the basis of Fresnel assumption. This is on the basis of Fresnel assumption. If light is moving obliquely, the effect is less than the light moving in a normal direction. Okay, the obliquity factor reduces the effect of light as the obliquity angle increases. So this is the second important point to understand the effect of the light wave at point P. Okay, I will come back to this off period elements. Now we have constructed off period elements, and we got this OP is equal to, if I write this distance, OP is equal to B. And what about M1P? M1 is here. This M1P is B plus lambda by 2. What about M2P? B plus 2 lambda by 2. This is M2. What about OM M3P? That is equal to B plus 3 lambda by 2, and so on. Okay. Now what I will do is, let us find area of off period elements. If you take first off period element, area of first off period element, that is equal to pi OM1 square, pi r square, pi OM1 I square, because this is first off period element. And this can also be written as pi. In order to write OM square, see this is O, this is P, this is M1, right? This is first half period element. I want to find this area. I want to find this area. And this is equal to pi. What I will do is pi OM pi r square is equal to pi into in order to write OMN square, I will write this as M1P square minus OP square. Okay, this can also be written as pi b plus lambda by 2 whole square minus b square. If you do this, b square plus 2 b lambda by 2 plus lambda by 2 whole square minus b square, and if you take this b square out, and lambda is very small, lambda by 2 square is still small, neglected. Then what we end up with pi, this 2 gets cancels, pi b lambda. So area of first half period element or zone is pi b lambda. Similarly, you can find the area of second half period element, means this. Right, this area is equal to pi OM2 square minus OMN square. This is equal to pi b plus lambda, 2 lambda by 2 means b plus lambda whole square minus b plus lambda by 2 whole square. If you do this, this is going to be 2b lambda. Again, lambda by 2 square is neglected and this becomes b lambda. This is also pi b lambda. Means, see, area of this first half period element, second half period element, this area, third half period element, all these areas are equal to pi b lambda. When you do this area we are going to get. What about radius? Radius OMN square. If you see this from this OMN square is equal to pi b lambda. Okay. If you write for pi OMN square is equal to pi lambda, pi gets cancels. If you write for OM1, you will get square root of b lambda. Similarly, if you do for second OM1 is square root of 1 b lambda. If you work out for OM2, then that is equal to square root of 2b lambda. OM3 is equal to square root of 3b lambda. You'll get this. So radii are proportional to square root of n into lambda. In general, OMN of right, square root of n b lambda. If you put n is equal to 1, you will get OM1. If you put n is equal to 2, you will get second radii of the second half period element. Okay, this is very important. Area is same, area of half period elements is same, but radii are proportional to their natural numbers. Next, in order to find the intensity effect, as I said, the obliquity factor, if M1 is the amplitude of light going from O, see this is O, this is point P. If for this light wave, M1 is the amplitude and this is M1 for this light wave going from capital M1, M2 is the amplitude. And for M2, this is the light wave. And then M3 is the amplitude. Then what happens? Light going from this point is the path difference between these two is lambda by 2. Means they are out of phase by 180 degree, like this. As I shown in this, if path difference is lambda by 2, these two are out of phase by 180 degree. If the path difference is 2 lambda by 2, that is lambda. If this is the third wave starting from this, then crest of this wave falls on crest of this. As crest of first wave falls on the trough of first wave falls on the crest of the other. Whereas here the crest of first wave falls on the crest of the other. These two are in phase. This is third wave. So for that reason, what happens? The amplitude goes on decreases at point P. If you draw the amplitude diagram, if this is M1, magnitude of the amplitude, M2 will be less than this. So what I will do is, I will write like this in opposite direction because they are out of phase. The third one is M3. Still it is small because obliquity factor is still more. This is M2 downward because out of phase. This is M3. Again M4 down. M5. This way. At point P, we are receiving the light waves from O with amplitude M1, from capital M1 with amplitude M2, from M2 with amplitude M3, and this is again M4. The even will out of phase with the odd ones, but even the amount, if you talk the magnitude also goes on decreases because of obliquity factor. For that reason, if you write M2 is in between M1 and M3, I can write M2 as M1 plus M3 divided by 2, average of these two. M2 is average of these two. So the total amplitude, if you write total amplitude at point O, at point P, at point P, that is equal to A, and this can be M1. I will take, if I take this as plus, then M2 is minus because this is out of phase. Again M3 plus because this is all odd are in same phase, even are out of phase with odd ones. Like this it goes on. It depends how many half period elements you will do. Okay, and this is equal to, I can write this as M1. This M2, I will write M2 as average of this. If I write like that, M1 by 2 plus M3 by 2 plus M3 minus M4, again I have to write M3 by 2 plus M5 by 2, like that. And if I am stopping at odd off period elements, say I will stop at now 3. Okay, you can stop at 5, at 7, at 9. If you do, then the resulted amplitude will be M1. This M2, right, you see this. This is M1 by 2. M1 can be written as M1 by 2 plus M1 by 2. And this M1, I am writing it as M1 by 2, M1 by 2 minus M2, M1 by 2 plus M3 by 2 plus M3 by 2 minus, this is minus, okay, this is minus, this is minus. So this becomes minus. And this cancels, this and this cancels. So if you are stopping at odd, then you will get M1 by 2 plus here if I take up to 3, then it is m3 by 2. If I take at 5, m5 by 2. What is left out is mn by 2. I will write if n is odd. Okay. If you are stopping for even, then a is equal to, say I have to take up to m4. Then what happens? It will m1 by 2 plus n minus 1 by 2 minus mn. Because if you stopping at 4, what you have to write is m3. You will write like this. m4 also, you are writing for m4 minus m4. You will write up to this. This is m1 by 2 plus m3 by 2 minus m4. So this is for n even. If you are stopping for even off period elements, 1, 2, 3, 4. Even, then this is the amplitude. Here 4, if you are taking up to 4, then you have to write m4 like this. But what if you see this, the m values are reducing. So which has got maximum effect here? That is from the light wave going from O. O has got maximum effect. The effect of all these light waves going from these off period elements decreases because of obliquity factor. So a major, these mn, if you are taking n is equal to 11 or n is equal to 15 or n is equal to 12, if that number is very large, then these mn values are small if n is very large. For that reason, this is a very important factor. So you can approximately, you can say m1 by 2. This is very important. The amplitude at P is m1 by 2. So what happens? The intensity, if you say it, which is square of the amplitude, then that is I is proportional to m1 by 2 whole square, or you can write mn square by 4. So the intensity is this. If there is only one wave going, if these other waves are not there, then this has got maximum effect, and that is equal to m1. But other waves are also reaching point P, then the amplitude is half of that. For that reason, if an object, see this, if an object has a size which is more than the half of the size of the amplitude going from point O, if the size of the obstacle for the light beam, if it has got a size more than half of the amplitude of the light wave going from O, then what happens? It is able to block the light reaching point P. Got this point? For that reason, what happens when an obstacle comes here, you don't see the light reaching at point P. Means a shadow is formed, right? And that shows the rectilinear property. Rectilinear property is observed. The formation of shadow is because of the light traveling in straight line. And if you have an object whose size is more than half of the amplitude of the light wave going from O, which is in a normal direction, to point P, then light is blocked reaching point P because of this. For that reason, we are going to observe the rectilinear propagation of light. If the size is less than this, then light is reaching point P, then only you are able to observe the bending of light ray. Okay, that is the explanation given by Fresnel for the rectilinear propagation of light. I think you understood this. Thank you goes to the notes I sent on WhatsApp group. And if you have any doubts, you can contact me. Thank you.